Well, good morning. It's 11:36, 6 minutes late getting started on the linear algebra course, but unfortunately nobody else is in the room but me. I've been taking care of some other things, getting set up, waiting for someone to come in, but no one is here yet. So I'll go on and get started. Hopefully at least one or two, three students will show up. Did want to say one thing before, no, I guess it's okay. I was just going to say they were going to remove, they have removed all unpaid students from the roll, but all three of you who have shown up at least once have paid, so you're in good shape. The one that we never saw had not paid, so she's been removed from the roll. All right, since no one's here, let's just pick up and go then. We're in Chapter 2, Matrices, 2.2, Properties, Properties of Matrix Operations, and we're at the bottom of page 52 with example 1. And it said, this is titled Addition of More Than Two Matrices. And basically it's following up with what we just talked about. Matrix addition is associative. It doesn't matter what order you do. And this will sort of be an illustration of that in some sense if you want it to be. Okay, here's a matrix. Actually, it's a column vector, 1, 2. You're going to add that to the matrix, a column vector, minus 1, minus 1. And add that to the matrix or column vector 0, 1, and add that to the matrix or column vector 2, negative 3. Sorry. All right. We're going to add those together and see what we get. Since you're adding the positions, you know, the numbers in exactly the same positions, it doesn't matter which order you add them. So if you're adding a 1 and a minus 1, that's a 0, plus 0 is 0, plus 2 is 2. And down here, a 1 and a minus 1 are 0, and 2 and a minus 3 would be minus 1. So that adds to be the column vector 2, negative 1. The reason you can add these, they're all exactly the same size, same dimensions, same everything, and you just add term by term. So a pretty simple example, but they had it in here, so we did it. One important property of the addition of real numbers is that the number 0 is the additive identity element, they call it. That is, any real number, C, added to 0 is always C. 0 is the additive identity element. For matrices, a similar property holds, especially, specifically, if A is an M by N matrix, okay, and O, Mn, okay, is the M by N matrix consisting entirely of zeros. Okay. I called it O because it looks like an O. You could also consider it the 0 matrix. Okay, in fact, that's the name of it. That is called the 0 matrix. Any matrix whose every element in the matrix is a 0. Now, if we're going to add it to an M by M matrix, then it has to be an M by M matrix. You can't add a M by N and add it to an O that's any other thing, you know, so all zeros, doesn't matter. It has to be the same size. okay? Then the same property holds that A plus O, or 0, is going to be A. If they are the same size, then you can add them and they will add to be A, because you're not adding anything else to them. So, for instance, O23 would be 2 rows and 3 columns. Every element in every row and every column is a 0. And when the size of the matrix is understood, you can denote the 0 matrix by O, which does look like an O, or, and they write it 0 bold. Now I'm going to put an arrow over it because bold usually to me denotes vector. This is not a vector, it's a matrix. Like that was a 2 by 3 there. Okay, that's not a vector, can't be a vector, but in order to distinguish between the O's and the zeros, I slash my zeros, so that's it, and I make it sort of like a capital 0, and since I can't write bold, I'll put the arrow over it as if it were a vector, but it's really not. Okay, so with that in mind, the definition of what a 0 vector is, 0 matrix is, let's show some properties of 0 matrix. So we're going to start off again. A is an M by N matrix. Okay? C is a scalar. Okay. Now, most of the time when we say C is a scalar, we usually don't have it being 0, but it could be. But think of it usually in terms of not being 0. But then the following properties are true. First of these, like we've already said, A plus the O vector that's also an M by N, and they designate it MN rather than M by N. Okay, that's always going to equal A. No way around it. Okay, it's going to be A. Because every element in O, and O is the same size as A, every element O is a 0, so whatever the element in A is, add it to a 0, it stays the same as it was before. All right, number 2. If you have the matrix A and add it to exactly the opposite of A, in other words, you negate every element in A. So A could have had plus and minus elements in it, sure, and zeros in it, that's fine too. But every one of them you change the sign, except of course zeros, which have no sign. And if you change every one and then add the two together, if it was a positive A before, it'll be a negative A now. If it was a negative B before, it'll be a positive B now. If it was a 0 before, it's a 0 now. Add all those elements together, and you're going to come up with the 0 matrix. And that will be an MN because A and negative A are both M by N matrices. Okay? The third one. Okay? If C times A is equal to the 0 matrix, MN, okay, if CA is that, then this implies that either, now I said before, usually we take it not equal to 0, but if this is the case, C is either equal to 0 or A is the 0 MN matrix itself, okay? One or the other, okay? Either C is 0 or A is the 0 matrix, okay? Those hopefully are pretty would follow what you would expect it to be. Now, they do have a little side note here. The second property illustrates, we already said that the 0 matrix of the proper size is said to be the additive identity element. Well, the opposite of a matrix is called the additive inverse of A. Minus A would be the additive inverse of A. All right. Now they're getting into a pretty similar thing, but a little bit different. They don't put this in terms of a theorem or other things, but it's just a comparison. The algebra of real numbers and the algebra of matrices have many similarities, and here are a few of those. This will be for real numbers. All right, good to see you. I sort of...
Sorry about Thursday. They had that 5-day capital meeting.
Right.
And that's why I wasn't no show for class.
Right.
I realized it would take that long.
Yeah. Yeah, it sounded like it was a pretty big deal.
Yeah.
All right. So congratulations on that, though.
Thank you.
Okay. By the way, I mentioned this earlier, but I didn't make many announcements because I wanted some students to be here first. They have removed all unpaid students from the roster, so we did indicate we had 4 in here before. Now it's down to 3 because one woman we never saw had not paid, and so they removed her, but not like we were expecting her or anything. She had never been here. All right, but you're here, and that's good. Let me do a couple of things first. Turn on the projector. I don't do place the bulb when it's just me in here, and flip the lights. So that way the projection will be a little clearer to see. And since I did put off and not do announcements until a warm body was here, now a warm body's here, so I'll do announcements. First of these is, if you're interested in this, I sure wish I could see it, but I can't. Today is the 24th, pretty sure. Yep, okay. And today, our volleyball team, I don't know if you realize this about our volleyball team, we had the very best season ever last year. We won more games than any volleyball team had ever won here at Lawson. And we got the same coaches and probably pretty close to half of the same players. And then I think they've done a good job recruiting some new players. So anyway, this evening at 5 o'clock, they'll be hosting Coastal Alabama Community College, the East one. Now, what the state has done, they've really been almost going crazy merging colleges together. So I can't even name the ones that now are Coastal Alabama. I know there was one at goodness, what's the name of the town? Is it Fairburn or Fair? Something another right down. There was a nice looking community college down there.
Oh, Fairhope?
Fairhope,
yeah,
is that?
Mobile, yeah, Fairhope,
yeah. Yeah, near Mobile.
Yeah, that's going to come out of Daphne and Fairhope.
Yeah, exactly. And I can't remember the name of the community college that was there, but that's part of Coastal Alabama Community College now.
Oh, that's a private university.
Yeah, Faulkner. Wait, there was a Faulkner State Community College, though. That was it, I think. All right.
When I go to Mobile, they have a billboard of other schools. I see it every time. I can't remember.
Yeah, so there were a lot of little community college in various.
Wallace.
Yeah, she was down there somewhere too. I don't know where Chattahoochee Valley is, if that's down there or not, but
Chattahoochee, that's right going, I think, about Atmore or after that. Well, it's east. It's on the east. It's
right.
Coming toward the east, southeast.
Yeah.
So it neighbors Daphne, Fairhope, Baldwin.
Right. Okay. So all those that were close to each other, they have merged into one college. But some of them had volleyball teams before they merged. So I think what they did, they just sort of combined them and let the East take one and the West take another, because we're playing Coastal Alabama. I'm sorry. No, there's a Coastal Alabama South as well. So I don't know if there's a West or not, but there's a Coastal Alabama. Anyway, the ones we're playing today is Coastal Alabama East, and that's over in the Birmingham West Campus, our West Campus. It's 5 o'clock this afternoon. So if you have the time and can do it, I'll be in class, so I can't do it. Go by and watch the volleyball team play. They're, I think, quite good again this year. I haven't heard anything specific. That's today. Tomorrow, they will be at Gadsden. That's an away game, Gadsden State Community College, and that'll be at 6 o'clock tomorrow. So that's Wednesday. Let's see. I'll tell you the rest of those next time. All right. I thought I turned that down, but evidently it didn't pay. All right. The College Scholars Bowl is currently recruiting players with knowledge in any subject, including history, literature, science, music, current events, mythology, and mathematics. I wish they would put mathematics after mythology, but anyway, we'll go on. So anyway, if you're interested in participating, it's a fun time, and you really learn a lot too. I can't think of any places that learning could be as much fun as that. Mr. Matthew West is the coach for the Scholars Bowl, College Scholars Bowl team, and his office is just down this half flight of stairs. The first classroom on the left is 259, then his office in 261. So it's wedged in between those first two classrooms on the left, but it's about midway down the hall. So it's real close. If you're interested, please contact him. He'd love to talk with you. Okay, I need to get rid of that one. It's over with. And the NASA's Community College Aerospace Scholars Program is accepting applications for the new year, this new season coming up, and the deadline for the applications are October 16th, which is probably close to 3 weeks away, but don't let it sneak up on you. If you're interested in participating, it's a great, great program. I've known several students who have participated, and they have loved it. They've gotten to do all sorts of really fun things. I know one time they actually were interacting with the space station and helping participate in an experiment up there. I mean, it was just pretty amazing.
Is it summer or is it a program or internship?
It's not really quite like an internship. It's somewhat similar, but it's the thing that you do activities with it, usually during the day when you can have time to do it. I don't think there's any stipend or anything, but in doing the activities, if you are some of the top ones, they get to go on some pretty impressive trips and they'll pay for those. So it's just, do you know Dr. Tracy Wilson, biology?
Yes, sir. She's my
advisor? Okay. Check with her. She's sort of the liaison to NASA. She can fill you in on everything. Or, on here are several websites that you can go to and find out more information there. Go.nasa.gov, and then there's several slashes that you can follow up various things. There's an e-flyer, a website, a video. They're all at https://go.nasa.gov, and then there's other suffixes after that you can go to the various places. So you're welcome to come take a look at this. NCAS. There it is, NCAS. NASA Community College Aerospace Scholars Program. All right. Now, before Charles got here, which was also before Keiston got here, I'd already done example 1 at the bottom of page 52, theorem 2.2 in the top half of 53, and just getting ready to do the just, I don't know what you call these, illustrations or something you might say, just between Theorem 2.2 and Example 2. And this is showing the similarities between the real number system, where you solve for x, and the M by N matrix systems, matrices they call them, okay, where you solve for the matrix, capital X, okay? And here's one. If you have this in real number system, if you have x plus a equal b, basically you subtract a from both sides, and you get x is equal to b minus a. Over here, if you had matrix x plus matrix a equal matrix b, now in this case, of course, before you can add any two matrices together, you have to make sure they're the same size. Identical dimensions, and they have to be, and then the b is going to be the same size as them. But if you do that, what you can do, now they say it slightly differently, is basically subtract matrix A from both sides, which is in effect, and this goes to 0 of course, the matrix X is then matrix B plus the opposite of matrix A. Now you could have done the same thing in the real number system and it works just as well, okay? So what that gives you is then X is equal to B minus A. It's the other way to express it, and why not just on and say it that in the beginning? I don't know, but they use an extra step there. So let us do something like that in example 2. Pretty simple and straightforward, I hope you'll find. So solve for x in this equation. 3x plus a is equal to b. Now when you see it named x, you sort of make the assumption you don't know. That's the unknown matrix. You don't know what the elements of that is. Now you hope to know the elements of A and B, and indeed you do. A is the matrix 1, negative 2, 0, 3. And B is another matrix, by the way, the same size, of negative 2, negative 3, 4, 2, 1. Okay? So with that in mind, what you can do is subtract an A from both sides of this equation, okay? Matrix equation. All right. And what that gives us is, those two A's add to the 0 matrix, 3x is equal to B minus A. Let's just go on and do that. What is B minus A? What would be the first element? Okay, okay, I've written down 3x, right? Okay, okay, a minus 3 from B minus A would be a minus 3 minus 1 is minus 4. Minus 3 minus 1 is minus 1. Yeah. Okay. Second element in B is a 4. Minus a minus 2 would be 6. 2 minus a 0 would be 2. And 1 minus a 3 would be negative 2. Very good. Now, if that's what 3x is, then you can divide by 3, which is multiplying by 1/3. So now we have x is equal to, and you can either leave the 1/3 on the outside and write the matrix like that, or you could write it as minus 4/3 to 2/3 minus 2/3. One way you can do it, and that's how they ended up too. I would have been perfectly happy leaving the 1/3 on the outside, 1/3 of -4/6 to -2, but they multiplied through and got -4/3 to 2/3 -2/3. All right. I apologize for my throat and my voice. I went to the UAB game Saturday and yelled too much, so sorry about that. Irritated my wife no end, but so now, so far here, section 2.2 are properties of matrix operations. We've dealt with matrix addition, which includes subtraction, scalar multiplication, which is multiplying a number by a matrix, and then properties of zero matrices, and then solving some simple matrix equations where you have an unknown matrix and you're just adding or subtracting matrices and then multiplying or dividing by scalars, like we just did. But the next subsection is going into properties of matrix multiplication, which are a little more involved, okay? Not quite the same as being analogous to the real numbers system, because matrix multiplication very different from multiplying two scalars. So the next theorem extends the algebra of matrices to include some useful properties of matrix multiplication, and they'll do property 2 below. The proofs of the others, they say, are in the exercise. Now, I know Keyston said he loved to do proofs, so he's got plenty of those he can work on there. So here's theorem 2.3, properties of matrix multiplication. So what we have is A, B, and C are all matrices. Now, here's what their little caveat here. They get away with murder with this one. With sizes such that the given matrix products are defined. I'm just going to say of appropriate sizes. Because remember, for adding and subtracting matrices, they've got to be exactly the same size. But when you're multiplying matrices, quite often they aren't the same size. Now, if they're square matrices, they're in the same dimensions. Yeah, those are fine. But if they're 2 by 3s, you can't multiply that by another 2 by 3. You can multiply it by 3 by 2, though, or 3 by 1, or 3 by 7, you know. So there are certain restrictions. So I'll just say A, B, and C are matrices of the appropriate sizes so you can multiply them. Okay? C is a scalar. Any old scalar. Okay? Then the following properties are true. Here's the first. A times BC, they claim, is the same as AB times C. Now, what I want to do next is assign some sizes to this. I'm going to be as general as I can be. So let's just sort of arbitrarily choose A to be an M by N. Okay? Now I can guarantee you, because of this relationship on the right, that B has got to be an N by something, right? So what letter you want to use? Let's not use M or N. Second? X? S, okay. N by S, okay? Now, if you're going to be able to do this, B times C and B is an N by S, then C has to be what? An S by something. But you get to choose what you want it to be. R, okay, a S by R. All right, so we've got this being an S by R and A being an M by N. Okay, let's see if this makes any sense. That's what we mean of appropriate sizes so you can do the multiplication. We haven't specified what they are, but we just know that the inner two here have to be able to do the same to be able to do that. The inner two here have to be the same to be able to do that. Let's see if the rest of it works out. If you did this, an M, an N by S by R, what's that going to be? N by R. Okay, so that product's going to come out being an N by R. I can't write. Okay? Now, that's an N. It's an ugly N. So let me see if I can clean it up some. Sure enough, you can multiply an M by N by M by R. What do you get as an answer? Say again? If you multiply M by N by an M by R, and M by R. So the left-hand side becomes an M by R. Over here, you multiply an M by N, that was A, by N by S, that was B. So this indicates that product is going to be in M by S. And then you multiply that by an S by R, and what do you get? M by R. So you haven't shown that the answer is the same, but you have shown that the sizes work. What the theorem is saying, yes, you can do this. So this would be the associative property of matrix multiplication. Okay, I'm running out of multiplication. All right, let's get those out of the way. Sorry. Okay. Number 2. Now, they're using the same letters, but they're not necessarily the same sizes, obviously, by the operations we're going to do. What they have here is A times B plus C. This is a completely different problem here. They claim to be, what would your guess be? AB?
Plus AC.
No, plus AC. In other words, it's like distributing the A over the parentheses. Now, obviously, that's bizarre, okay? So let's start again with A being a M by N. So this is an M by N. This is an M by N. Okay, we let that be the same as the A before. Now, from your first relationship on the right, what does that tell you B has to be? At least one dimension of it. B would have to be at least one dimension. What would B have to be? If you can multiply A by it, N by something, right? So you want to choose something to call it? T? N by T. Okay. Now, over here, since you're adding these two, that would imply, since B is an N by T, C would also, in order to add them, it has to be an N by T. So I said, don't make this assumption they're the same sizes as above. They can't be, okay? So that's why it says at the top, of appropriate sizes so the things will work. Okay? Well, if C is also an N by T, you can multiply it by A, which is C would be an N by T. And sure enough, if you add two N by T's, what do you get? An N by T, because you're adding, okay? Okay, so you're multiplying an M by N by an N by T. Is that multiplication valid? And what would be your result? M by T. Okay, well, let's see what we've got here. On the left here, you have AB, which is M by N times the N by T. So the N's basically cancel out. So you have an M by T. I don't pick up the pen, it drags. Okay. That's an M by T. In similar with C, A times C would also have to be an M by T, which is very fortunate because these two have to be the same size to be able to add them. And sure enough, they are the same size, and they're both the same size. When you add them, they'll be that same size in M by T. Now again, this doesn't prove anything about the numerical values, but it just tells you the sizes match, they work. The theorem is saying the numerical values do too. But I'm just justifying for you that the sizes do work. So that was the second. That's sort of like what is the distributive law of matrix multiplication over matrix addition. So let me write that down. Distributive property of matrix multiplication over matrix addition. Sorry. Number 3. Okay. Sort of the other way to look at that, A plus B times matrix C, what would you guess that would be? AC plus BC. And that's also a distributive property of matrix multiplication over addition. Okay? Only this time you have the addition in front and the multiplication afterwards. Now, different sizes, okay? Again, don't expect them to be the same size as either of the first two. Let's look at them separately. You want A to still be an M by N? Okay with that? What does that make B? M by N as well, because you can't add them unless they're the same size. And that, what would that make C at least one of its dimensions? What? N by something. What do you want that something to be? A? Okay. It's little a, just don't confuse it with the other A. Okay? Yeah, right. Okay? So when you add these two together, adding two M by N's, obviously you'll get an M by N. And then you multiply that by an N by A, and the N's go out, and you'll wind up with an M by A. It's not quite an MBA, but it's close, okay? Well, if A was an M by N, and C was an N by A, B was a M by N, C was an N by A, then this would give you two middle ones are the same. I can hardly read my writing. And the product would be an M by A. Here, the two inners are the same, and you get an M by A. And you you add two M by A's together, you get an M by A. So yes, at least dimensionally, this one fits too. And this is just telling you, the theorem is telling you, numerically it'll come out the same as well. Okay, no reason to expect it won't. All right, that's the third one. Let's look at the fourth one. Let me erase some of these down here because I don't have room without them. And that's also a distributive property of matrix multiplication over matrix addition. And number 4. If you have that scalar C times the product of AB, what do you think that's going to be? Again, tree product, so you can do CA times B, and that's also pull the A out times CB. Okay, so you've done a couple of different things here. Here you associated the constant with the first matrix and multiply that by the second. That's legal. That's an associative property. But then you also commuted the C and the A, which is okay too, and then grouped the C with the B and had A out front. Okay? Let's see what dimensions they have to be. C, of course, is a number. So it has no dimensions. It's just a number. A, you want that to be an m by n like we've had it? What would that make B have to be? An n by something? What you want that something to be? Well, what? We already used m. That's an m by n times an n by something. Pick a letter. Second?
T.
T. Okay, T would be perfectly fine. Well, C is just a scalar, so when you multiply these two together, you get the n's are the same, so you get an m by t. Multiply that by a number, you get an m by t. Okay? So this is still an m by n. Now you can multiply a scalar times any size of a matrix. It doesn't have to be the same size. So that stays at m by n. This b was an n by t. And of course those two are the same, so you get an m by t. That's fine. Over here, a was an m by n. C was a scalar times b, and b was an n by t. And we'll, so C times an n by t is still going to be an n by t. It's just every element in B is multiplied by C. And then these two are the same, and you get an m by t. So yeah, the dimensions work out. This is telling us the numerical values also work out quite nicely. So this is an associative property of a mix of scalar and matrix multiplication. Okay. Again, I don't think there's anything too earth-shattering about that. But notice here, the one they have left out, we have associative distributive. What are we missing? Commutative. You cannot commute matrix multiplication. You just can't. Never. Okay, well, I don't want to say never. We will run into one special case when you can, and that's going to be a very special case. But in general, you cannot commute. So you can associate and distribute within certain bounds, as long as your matrix sizes work out, but you can never commute. Okay. Now, the proof for this one, I think this is number 2. This is very indicative of how proofs go in matrices. And they can get sort of long and hairy, but if you follow them through, you usually change a matrix to the representation of the little aij's, okay? And and go with that and show that the combinations always then turn out the same. Remember, you usually say the A will be, the elements in that will be little a, ij. I will be one of the M rows and J will be one of the N columns, okay? Numbers within that. B, those elements would be little b, and then if I were doing it, I call this J by K, because the N, so the J, so, same as before, okay, and C would be N by J, so that'd be little c, and then, but if you wanted to use totally new letters, you could do that as well. Okay. I know that Keystone can't wait to sit down and do that proof. Okay, let's move on to example 3. We won't prove anything, we'll just do it. Find the matrix product ABC by grouping the factors first as AB and then multiply by C, and then later we'll do A times B times C. Okay? Show that you obtain the same result from both processes. So here is A is 1, negative 2, 2, negative 1. B is 1, 0, 2, 3, negative 2, 1. All right. C, keep hoping they'll get smaller. They keep, well, no, it's not any bigger. I'll just think it's a 3 by 3. Negative 1, 0, 3, 1, and 2, 4. All right. What we first want to show is that we want to multiply and see what AB times C is. So the first thing we've got to do is AB. Can you even do AB? What size is A? 2 by 2. What size is B? 2 by 3. Yes, you can, because the inner 2's are the same. What size will this turn out being? 2 by 3. So, yeah, it'll have 2 rows, 3 columns. Okay? To get the first entry, which is the 1, 1 entry, you take the first row of A times the first column of B, and what do you get? I couldn't hear, sorry. Okay, you get a 1 minus 6 is minus 5. Perfect. Okay? The second entry is a 1, 2 entry, so you take the first row of A, second column of B, and what do you get? 4. Perfect. And then the 1, 3 entry, first row of A, third column of B, and that gives you, you get a positive 2 plus a negative 2, and that gave you 0. Okay? The 2, 1 entry, second row of A, first column of B. Negative 1, perfect. The 2, 2 entry, second row of
2.
Okay, what you get? 2? Perfect. Okay, and then the 2, 3 entry. 3. All right, good deal. Now you got to multiply that by C, okay, which is minus 1, 0, 3, 1, 2, 4. Okay, now, can you even do that? What size is AB? 2 by 3. Can you multiply that by what's this new one? 2. Goodness. Say 2 and write an X. I don't know what's wrong with the brain. Okay. Whew. This is a 2 by 3. Wait, 3 by 2, sorry. 3 rows, 2 columns, 3 by 2. And sure enough, you can multiply them because the inners are the same. And what size are you going to have at the end? 2 by 2. So the 1-1 entry, sorry, for some reason I can't breathe now, so excuse me. Okay. 2 by 2. So the first entry here is first row, first column. What does that give you? 6 plus 7 is 13. Is that what you said? 5. I'm sorry. Wait a minute. I'm off. Let me start over. Okay. I just lost something. Okay. 5 plus 12 is 17. Sorry. I was doing something else. And 0. Okay. And then the 1, 2 would be first row, second column. What would that give you? 4. And that's all. And then the 2, 1 entry is second row, first column. 1 plus 6 is 7. Plus 5 is... Wait, plus 6 is 13. Goodness gracious. The old gray cells there. Okay. It's 1 plus 6 plus 6, 13. Right. And then the last, second row, second column, 14. All right. So there's your first multiple. Okay. The second one is to check and see what A times BC will be. So, of course, we're going to start this and do A times the product of BC. So let's do what BC is. Well, B is a 2 by 3. C is a 3 by 2. Let me wipe out my wipeouts. Okay, and here, since the 3's are the same, you can do it. So what size is BC? 2 by 2. Okay? Wait, sorry. Oh, man. All right, so let's do that one. The 1, 1 entry is first row, first column, and what would that give us? Negative 1. What did you say? Negative 1, right, is the first entry, plus 0, plus 4. Negative 1 plus 4 is 3, isn't it? Am I doing something wrong here? Negative 1 plus 0 plus 4. First row, first column. Okay, 3. Okay. The 1, 2 entry would be 8. That one was easy. The 2, 1 entry would be negative 7. And the 2, 2 entry would be minus 2 plus 4 is 2. All right. We're going to take that one and multiply it by A, which I'll write it here since it's so far away there. 1 minus 2, 2 minus 1. Okay. Multiply those two, and, okay, what size will you get out of that? 2 by 2 by 2 by 2 is a 2 by 2, right? Middle 2's are 2's, so that's it. You get a 2 by 2. So let's do that one. The 1, 1 entry, first row by first column would be would be
17.
17. You get 3 plus 14 is 17. Then the 1, 2 entry, first row, second column would be 4. And 2, 1 entry, second row, first column would be 13, exactly. And then the 2, 2 entry will be second. Okay, that would be 16 minus 2 is 14. And look at that. These two are indeed equal. AB times C is the same as A times BC. They're identical. Now, just because these are doesn't prove they all are, but we've already had the theorem stating they are. This just sort of verified it for you. Okay. All right, there, I lost where we were. 17, 4, 13, 14. Got it. Now, what we have stated earlier, we're now going to verify this. It was about commutativity. What you think on matrix multiplication? Is it commutative? No, we think not. Okay, let's try AB and then BA given these two matrices. Matrix A is, let's see, I think I'm going to scoot this over some. Okay, matrix A is 1, 3, 2, negative 1. And matrix B is 2, negative 1, 0, 2. Okay, so let's first calculate what AB is. First, can you do it? Yeah, 2 by 2 by 2 by 2. Sure, you can multiply those. The middle twos are the same, and your product is going to be 2 by 2. Yuck. Don't. Okay. Now, goodness, I'm getting dry in the throat. You'll get a 2 by 2. First entry is 2, the 1, 1 entry, so first row by first column is going to give you what? 1 times 2 is plus 3 times 0. First row, first column. First row of A by first column of B. 1 times 2 is 2. 3 times 0 is 0. So that's just going to be 2. Okay? The 1, 2 entry. First row of A, second column of B. That would be 5. And 2, 1 entry. Second row by first column. 4. And the 2, 2 entry, second row by second column, negative 4. Perfect. Okay. Now we want to compare that to BA. This is AB. So BA would be, there's your B. I'm going to multiply it by A. I'm going to bring the A over here. 1, 3, 2, minus 1. That way it'll be easier to see. Can that be done? Sure, it's a 2 by 2 by a 2 by 2. And this time we're going to wipe out the innards, not the outers. So, sure enough, that'll be a 2 by 2, if you can read my ugly writing. Really? First row by first column, 1, 1 entry. 2 times 1 is 2. Minus 1 times 2 is minus 2. 2 minus 2 is 0. Okay. The 1, 2 entry, first row by second column, would be 7. Perfect. The 2, 1 entry, second row by first column, 4. And the 2, 2 entry, second row by second column, 2 or negative 2. All right, negative 2. All right, what you think? Commutative? Nowhere close. It's just happenstance that one entry is the same. Most of the time, nothing is going to be the same. No. Matrix multiplication is not, in general, is not commutative. Okay? When you do have commutivity, you have very special matrices on your hands. We'll talk about those later. Okay? Now, they do give you 2 matrices that make that happen. So, let's do it. I think I'll erase because otherwise I'll run out of room doing it. We're going to do another AB. I'm just going to erase them all and write everything down again. This time we got A equals 1, 2, 1, 1. I'll add it as a 2, don't confuse it for a 3. B is negative 2, 4, 2, negative 2. Let's do AB here. Can you do it? Sure. 2 by 2 by 2 by 2 is a 2 by 2. And the first row, first column will be a 2. Yes. Negative 2 plus 4 is 2. First row, second column will be a... Really? Now, remember that is a 2. It's my pen drug. Okay, try that again. First row, second column. Okay, 4 times 1 is plus a 2 times negative 2 is
0.
Yes, it'll come out 0. Okay. Whew, goodness, I'm feeling almost dizzy. All right, the 2, 1 entry, be second row of A, first column of B. That would be a first row of A, first column, no, second row of A, first column of B.
It's going to be lost the bearings.
What's that?
I lost the bearings on it.
Okay. It's the 2, 1 entry, so it's second row of A times first column of B. 1 times negative 2 is? And then 1 times 2 is?
2.
Plus 2. Negative 2 plus 2 is?
Oh,
0. Okay. And then the 2 entry, second row of A by second column of B. Second row of A by second.
Amount to 2.
2. Okay, I'm sorry. If you said it, I can't hear.
I didn't say it. I always said it the first time.
Okay. All right. Now, let's try BA. And just for funsies, I'll go on and write the A over here again. 1, 2, 1, 1. So it'll be easier to multiply. Is that able to do? Yeah, 2 by 2 by 2 by 2 is a 2 by 2. Okay. So first entry, the 1, 1 entry will be a is what? Negative 2 times 1 is negative 2 plus 4 times 1 is 4. Negative 2 plus 4 is, you're adding negative 2 plus 4,
6.
negative 2 plus 4. 2. Okay. Now the 1, 2 entry, first row of B, first column of, second column of A. Yeah, that's it. First row of B, second column of A. Okay. Negative 2 times 2 is? 0. No, negative 2 times 2 is negative 4. And then 4 times 1 is? 4. Negative 4 plus 4 is? 0. Okay. 2, 1 entry. Second row of B, first column of A. Second row of B, first column of A. 2 times 1. Negative 2 times 1.
4.
Negative 2 times 1. Negative 2 times 1. Negative 2 times 1.
Oh, negative 2 times 1 is 2.
Is, no, it's not 2, it's negative 2.
Oh, negative.
Negative times plus, okay. So you got 2 minus 2 is? 0. All right. And then the 2, 2 entry, second row of B times first, second column of A, that would be a? It's what? A 2 again. Perfect. They are the same. My word. Here we have two matrices that are commutative. Now, those are special matrices. Now, number one, if you look at B, you can factor a 2 out of every term of B. And that would leave you with a minus 1, 2, 1, minus 1. Okay? Okay. Now, those two matrices, this one and that one, they have a lot of similarities. Okay? And later we'll see what difference that makes. Okay? And we'll find something very special about them. But just hold that thought. We're not ready for it yet. Okay? That was example 4. I don't think we have time for example 5, do we? So let me mark that we'll start with example 5 there next time. And I thought for sure I brought up with me my eraser. Maybe it's still in my pocket. Yes, it is. Okay. So we'll begin with example 5 next time. All right, we almost, well, no, this is a long section. Yeah, a pretty long section. Think you can do any of the odds 1 through 5. They're all at Calc Chat. I think you can do any of the odds 7 through 11. They're at Calc Chat. You can do 13. It's at Calc Chat. You can do any of the odds 15 to 19. They're all at Calc Chat. You can do 21. It's a Calc Chat. 23. It's a Calc Chat. Think you can do 25. It's a Calc Chat. Okay. Maybe we'll hold off there and pick up there next time. Okay? Any questions? Okay, I think today we were entirely in 2.2, weren't we?
Yes, sir.
All right. Let me go.